Welcome to chapter 3 of our telematics course. This chapter covers the physical layer. Physical layer, here our lowest layer in our reference model. So the physical layer, that's the first layer we start, and then from physical layer we go up to link layer, network layer, transport layer, application layer. So starting with layer 1, 2, 3, 4, and then ending up here at the applications. You know already some application layer protocols, and we'll further extend this to some new applications. Okay, so in the last chapter at the end, I promised we will open the black box. We go down the layers, starting here at the physical layer. We know we have all these fancy applications. Okay, maybe they look a bit different today, but in the end, all those applications, they rely on the application layer protocols. We saw 4 of them in the last chapter. But the main question is, so how in the end do we transmit something? We know up there in the applications, the application layer, well, we have our data, our applications, and then we have several communication protocols. But in the end, really down here, we have physics. It's called physical medium. So there is nothing, the space or a cable or a fiber. So radio transmission, optical transmission, these are topics here. So that's the idea. We start here. And on top of this physical medium, sometimes people call this also, this is layer 0. We have the physical layer. And physical layer, the main job here is a bit per bit communication. What does it mean? Well, we insert here our ones and zeros, whatever exactly the bits we operate with in our computer. That's what we know from the computer. So this is the input, and then the physical layer does something, and that's exactly what we'll talk about in this chapter. Sending over this data somehow over the physical medium through the network, and then we go up through all the layers. So bit per bit communication. And the other way around, if a signal, as we call it, arrives via physical medium, then the physical layer does something, and the result will be a bit stream, ones and zeros. So that's the idea. On top of that, that's the next chapter, we talk about the link layer. And this is the idea here. We want to send frames. So whole packets here, they are called frames, and they should be error-free. We send them, receive them, and if there are errors, we have to do something. We also take care of the so-called medium access control, so what happens if several participants want to use the medium. On top of that, we have the network layer. This is where we have our internet protocol, IP. We talk about formats and addressing, etc. On top of that, the transport layer. So here we have a real end-to-end communication from one process to another process on hosts. We'll talk about congestion control, flow control, and we will have a look into different protocols. On top of that, this is something you should know. This is our application layer where we have our DNS, SMTP, HTTP, SNMP, and some others. So the whole idea here is that we can run many different applications on top of this protocol stack, and the protocol stack should be neutral when it comes to certain applications. So here the network layer shouldn't care about what's going on top of it. Link layer should simply get some frames and generate bit patterns, then hand it over to the physical layer. And the whole network itself also should be neutral when it comes to different applications. We'll see that sometimes this causes problems. So think of real-time applications, videos, etc. that require certain quality of service from the network. We'll discuss this. So if you look at the layers, well, you know that in the application layer, we're talking about who's standardizing this. So it was the World Wide Web Consortium, in the case of HTTP, and especially the IETF. For layer 4 and 3, this is also mainly the IETF. And layer 2 and 1, among others, it's for example IEEE. We'll see examples for this. Okay, so this is a bit abstract. These are layers with certain concepts. We'll dig into all these layers, but so where are these layers? Now, if you have a look at your computer, so where are the layers in your computer? Well, this is a simplified diagram showing a client and a server. So basically what you have is a process running on the client. So process, and this process can access the kernel via so-called system calls. You can have a look at our bachelor level operating system courses, giving you some more details here. And the same as here on the server side, you have server processes also talking to a kernel via system calls. So client and a server, and they want to talk to each other. But we all know all this, well, connection requests and acknowledgements, data transmission, disconnection, just an example. This has to go through the whole protocol stack. But where is it? So if we have a closer look, then typically layers 1 and 2, they're in the network drivers. So drivers, this is basically a piece of software that runs on your machine, and this software handles all the access to hardware, network adapters, for example. And this software helps, for example, sending, receiving bytes, transmitting them from a buffer from your main memory to the network adapter and back. So drivers are important to adapt the hardware to the operating system. And for many operating systems, drivers are considered a part of the operating system. This is not necessarily the case, so there are microkernels, etc., where this is all outside the kernel, but typically for the big operating systems like Windows and Linux, etc., the drivers are part of the operating systems. So drivers, and the drivers are typically, they come with the hardware, with the special network adapter or graphics adapter, etc. So this is where you have layer 1 and layer 2, especially layer 1 is typically implemented in hardware. Also parts of layer 2 can be drivers plus hardware, firmware, so it depends on the design. Layers 3 and 4, part of the protocol stack, so IP, TCP, UDP, etc., inside the kernel for many operating systems. So all this is then controlled by the kernel. And if you go up, then typically layer 5 and all the apps, they are in so-called user space. So there are different protocols up here and then all the applications. So for most operating systems, the protocol stacks, at least layer 3 and 4, are part of the kernel. Also the drivers are part of the kernel, and for microkernels can be outside. So, and there are also implementations where the protocols layer 3, for example, if you participate in mobile communications, I will present something about ad hoc communication, and there are some protocols, you can implement them also outside. So there are different types of implementations. This is just a very common scenario. So now we know where it is and can go back to our layers. So just another abstract look on the layers. This is important for you to understand. So if we have this very simple setting, so with our applications, they run on top of a layer 5 and layer 4 and layer 3, etc. We have many intermediate layers, and then there's a lower layer. This is typically our layer 1, the physical layer. And if you want to communicate between the peers, that's our horizontal communication, what we always have to do is we go vertical. So we go down through all the layers. That's the typical scenario. The application does something and you want to send. You go through all the intermediate layers. You go to the lowest layer and then you go through the network and up again. So this is vertical communication, and we have always service access points, and the higher layers, or for the top layer, the application, they consume a service from this service access point, so you can send something, you can receive something, so you use the service of a lower layer. And this goes down, so all the intermediate layers, they always use services from lower layers. And even the lowest layer, well, basically here we will see you have a cable and a plug, etc., etc. So, well, that's not really a service in a computer science sense. But okay. And the other way around, basically the lower layers, they offer services to the higher layers. At the service access point, you always offer services to higher layers. So that's the idea. Okay, so the real communication is this vertical communication between the layers, using services of lower layers, offering certain services to higher layers. But what we want to have, this is our virtual communication, that's the peer-to-peer communication, so the communication between peers. So one application talks virtually, that's a horizontal communication, with another application. So that's the idea, and only peers talk to each other. So here, intermediate layer talking to a peer at the same intermediate layer. So layer 4 talks to layer 4. And it's not possible for an application, for example, just to directly talk here to a medium access control on layer 2. So this will not work. They don't speak the same language. They don't know what the packets mean, what the bit patterns mean, etc. So that's the key idea. So that's something we handled in chapter 1, just for you to remember. So coming back, on the title slide you saw this little diagram, and we'll use this for each of the chapter just to indicate where we are. Here we are down here at the physical layer. We also typically use the term hosts for the end systems, so this could be embedded end system, your PC, a laptop, a mobile phone, whatever. And the host always implements the complete stack. So from the physical layer to the application layer, and the host then hosts the applications. And then in between, we can have, for example, as shown here, routers. So in the network, we will have routers, intermediate systems, and they implement routers, for example, the stack only up to the network layer. We will also learn a bit more about switches. They implement everything up to layer 2, and repeaters only layer 1. So there are different types of intermediate systems. Okay, so hosts, routers, networks, layering. So please do go back to chapter 1 if you're not sure what all this means. Okay, now let's start. In this chapter, we will handle all these physical things. Well, we will not go too deep into this because this is a computer science course and not electrical engineering, but also computer scientists should know something about signals and bandwidth, etc., quantization and encoding, modulation. Why? Because the real world can create errors. There's interference, bits may flip, etc. And if this happens, our higher layer, they have to fix it. Nature will not fix it. So we have to do something. We have to program certain algorithms that fix bit errors, that detect that something went wrong, that detect where a bit starts, where it ends, where a frame is, what a data packet is, etc. So we have to know a bit about this, also that we learn that our higher layers, they have to be flexible, they have to adapt to different data rates. And we will learn why we have different data rates, what are the limitations. So you should know a bit about this. So we start with signals, bandwidth, symbol rates, and just with an example. And what is this, a signal at all? And how can we compose certain signal types, etc. So, an example. So this is something written by Johann Wolfgang Goethe, and we want to transmit it. So what do we have? We have the text, something written. We have something to transmit something, so we have a sender. So in the end, we have a piece of data. we have a sender, so that's the sender, and we have a receiver. The main problem is that the receiver doesn't know what the sender wants to send. This is what we have communication for. So now let's focus on one part, Goethe. Okay, we want to transmit this. So maybe you cannot write what Goethe has written, so we already mapped this, so G, O, etc. to these letters. And so that's one of the first things we have to do. So we have to separate what we have here in this example, on this note, we have to separate this into certain characters. Okay, so certain parts of our data that can be separated. And the next step is we have to encode it. Why? Well, we have to be able to distinguish it. And why can't we send a G? Well, because here our sender is very limited. So in the end, what we have here is light on and light off. So that's it, light on, light off. And this can be, for example, represented by, well, our ones and zeros, etc. So we have to encode the G, we have to encode the O, and we have to agree upon the rules how we then translate the ones and the zeros into a signal. So maybe the ones are bright, shining light. So you see here 2 times light, and the zeros are no light. Okay, sounds very simple. Okay, light, no light. Yes, but now you see, as soon as we introduce certain coding, the problems may begin. Okay, looks simple, but how to identify the gap? So maybe you agree that the gap is no light. But then what's the difference between a gap and no light, because there's a zero? And how to encode the gap between the no light zeros, so if the gap is also no light. Okay, so we also have to talk about the duration of these symbols. There's light on, light off, there's no light, and whatever is in between. So you see, this is a very simple example, and we can code also the O this way. But what does it mean? Light on 3 times. Does the light stay on in this case? So it's all the time light on. And how do you transmit the length, the duration of this light on? Let's call it a bit or whatever. So the duration. What happens if the receiver here doesn't know the duration? So how do you transmit the duration? We call this then also synchronization. So we have to synchronize sender and receiver. So how is this performed? And then also we have to, well, receive, and we have to understand what it means. So, okay, how to implement the brain? That's a complicated question. We as humans, well, we can do quite a lot with our brain, but now let's stay with very simple technical systems. So, why is our world of communication a bit more complex? Because many things can go wrong. So what might go wrong? This looks very simple. Well, think of the scenario, you know, you have this text from Goethe and you have this flashlight, and now you encode it with light, 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 and darkness, darkness. And then there's some fog in between. So there's fog, and this fog creates, now example, noise or attenuation. So the signal gets weaker and weaker and weaker. What will you receive on this side? So, can you still see that this is light? Or where's the threshold when suddenly everything is darkness? Because this is too dark. So there's a certain threshold, and from this point on, maybe this is darkness. So, because if you think that you transmit here over time, let's say the signal strength, that's how bright the light is, then maybe you start with bright light, bright light, bright light. These are our 3 times this. And then you continue with 2 times darkness. These are our filled circles. Okay, so 1, 1, 1, 0, 0. So this is the capital O. Okay, but now if the fog comes, maybe the signal is weaker, only like this. Or if the fog is even stronger, the signal's like this. So where is your threshold when you then decide now it's really dark? Because there's not only fog, but maybe there are some other flashlights. Maybe there's a campfire somewhere. Maybe there's headlights from a car, whatever. So that means maybe black is also not black. So it's gray, it's somewhere in between. So when do you say it's a 1, when do you say it's a 0? And we will see this is not that easy. Then we have problems like collision. How can this happen? So you send data. So for example, you send first your G, then your O, whatever, and they may overlap. How can this happen? Well, think of that we use here electromagnetic waves, our light, and they travel at a certain speed. And now you could, for example, have a situation where here's someone and here's someone else, and you send your data, whatever, your light, and the light is reflected. Now let's assume maybe mirrors, buildings, or whatever. And so it takes a bit longer for the signal from the sender to a receiver. And now the receiver moves a bit up, and suddenly a signal you send later can go straight through to the receiver. A straight line, the so-called line of sight, is always the shortest. It's shorter than the path the signal takes when it's reflected. Very simple example. So you move, and suddenly a signal you send later may overlap. And if you have overlapping signals, this will create, in this case, a gray value, or at least this is not a clear 0 or clear 1. Yet another challenge. And we will see that even in fiber optics of today, we have this problem. What else can happen? Well, maybe due to many effects, and I will show you some, your synchronization will be challenged. So you see some of these bits will be closer to each other, the gap might be wider, etc., etc. So there can be very strange effects. The problem is at the receiver side, maybe you do not know when a bit starts, when it ends. So how to keep the receiver in sync? So that's a big question. And we will see that there are ways of transmitting data that actually carry the synchronization together with the data. And then there are other ways that where you do not have the synchronization, you need a separate cable for synchronization. Okay. So you see, even with this very, very simple example, there are certain challenges, and all these problems, they appear in real communication systems. So now I already talked about, well, this could be light. So you have some sender, and then this light travels to the other side. So these are, generally speaking, our signals. And then the question is, what is a signal? Okay, so what is it? Well, I touched this already briefly in chapter 1, that right now where a signal is the physical representation of data. So if I want to transmit to you the word data in this example, well, I use signals. In this case, you see white pixels, and then there are black pixels and white pixels again. And okay, somehow you compose this in your eyes and brain, and then you generate this abstract word data. We will learn that there are different types of signal. We will learn something about analog signals, continuous values, and digital signals, discrete values. And for the moment, it's okay to see that, okay, analog signals, these are these wild signals, where at, well, continuous points in time, you have a value out of a certain interval, continuous. So you can pick any of the values. So basically, you have a interval in our real numbers. So you can pick any value. And we say, okay, the world around us, that's analog. Because brightness and colors, etc., they all come in continuous values. We do not talk here about Planck size and Planck time, etc., and quantum effects and all these things. So for us, the world is analog. At least, I mean, the systems we use today. And our digital signals, this is what we use in the computers. So this is where we have this clear 0 and a clear 1 and a 0 and a 1. So we have discrete values. So this maybe is plus 3.3 volts. And this is 0 volts. So very discrete values. So with a sequence of discrete values. And we will see what we have to do if we translate analog into digital and digital into analog. So our physical medium, the world around us, is analog. Our computers, they're digital. So we have to translate. And that's part of the job of the physical layer. So how does it look like? So we have a sender, we have a receiver, and we have a physical medium, access point. So in the end, this is our layer 0. This is a layer 0. And we know this is where we have nature. And this might be a plug and cable, etc. So depending on what you use, copper wires. We'll come at the end of the chapter back to this, what type of copper wires and fibers we can use. And we have a transmission channel. And this channel has certain characteristics. This is not an ideal channel. We have interference, we have certain what we call bandwidth limitations, etc. But we know up here in our computer we have our data, our ones and zeros, and then the physical layer has to do something to convert this into a signal we can transmit. So that's the idea. So here, down here, we have our wires, we have fiber, we have radio communication, so the space around us. So, different media, and they have different characteristics. What is quite obvious, we cannot use the same type of signal. What this means, I'll come back to this. For example, the same type on optical fibers we use on a copper wire. Doesn't work. So, different types of signals we have to use, different frequencies, etc. We also have to specify and standardize how do we represent data? How do we represent them here down here in the signals? So voltages and different codes, etc. So yeah, that's something that has to be specified. Otherwise, in worst case, we have a shortcut and a problem in our computers. And yes, we also have to specify certain mechanical electronic aspects, so plug designs, pin usage, etc. Not focus in this chapter. So layer 0 here, and we will focus here on layer 1, the physical layer, what's going on here. But we have to know something about the lower layers. So what do I want to teach? So one of the goals is to give you an idea where certain fundamental limits come from. Because the point is, we cannot transmit arbitrary signals over whatever medium. So try to transmit light, for example, over a copper wire. Obviously, doesn't work. So, okay. So there are some properties of the medium, and there are also some properties for the propagation of electromagnetic signals. And we have to follow what physics, what nature gives us. So, where are the limits here? And then we know something from math. So how do we encode data? So you have to understand this. And then the second goal is, I will show you certain techniques, deployments, how we try to approach these limits given by nature. So it's quite obvious. Well, we cannot have, at least right now, 100 gig, 1 terabit per second over a mobile phone. But why? Why doesn't this work? Where are the limits? So why can't we transmit 1 petabit per second over a copper wire? So there must be a reason. So how did all this start? Well, basically, there are many different people claiming they were the very first coming up, the inventors of the phone, of the telephone. So here you see how it started: analog signal, acoustic signal, converted, what's typically called a microphone. So these are different pressures in the air converted into a signal by the microphone. And on the receiver side, you again have a converter, a loudspeaker, converting these signals into, again, differences in air pressure reaching then our ear. So that's the core idea. Okay, so this is how this all started, using a cable transmitting analog signals. And as I told you, the word, our cable, that's analog. That's typically analog. So we still have to use some analog signals for transmitting our data. Okay, so, but our computers, as I told you, they operate with digital signals. So what do we have? Well, we have our computer, abstract, so our data, but also in the computer we represent this. So we will see, this is so-called line code, how we do this. But then we have to go to a so-called codec, a coder and decoder. So in this case, first we have to code it in the network interface card. So we generate a type of a signal out of the digital signal that fits to the physical medium. So this is then an analog signal with certain characteristics. We will have a look in what the characteristics are. So that's the idea. So the physical layer takes data 1 bit at a time, 1 or sometimes several bits at a time, encodes it and sends it over the medium. On the other side, you take the signal and somehow you have to create a digital signal out of this, also in the decoder now. And this then represents our data. And hopefully it's the same. Oops, no, it's not the same. What do we do here? Well, I can tell you right now, already, the physical layer will do nothing. Physical layers, they don't care about errors. This is something left For the higher layers, layer 2 will take care of this. So obviously we have to convert. We have to convert digital to analog signals and vice versa. So the computers, they deal with the digital data, discrete signals. The medium, well, is analog. So continuous signal. So we have to convert from digital to analog somehow, and vice versa. And this is called quantization. When we go from an analog signal then to a digital signal. We'll see how this works and where the problems are. And we will also learn we need something in addition. We have to measure. We have to measure why? Because if we have an analog signal, like here in this, on this side, on the receiver side, computers cannot permanently follow all these values. Computers check values at discrete points in time. The physical medium, this varies all the time, but we will check only at certain points in time. So quantization and sampling, this will be the major focus in the next subsection. But before we start with this, well, some questions, some tasks. If you have problems understanding the key ideas of layering, protocols, interfaces, data packets, etc., please go back to the introduction or to the bachelor course. Then some questions. So if you look at the peers, can you directly communicate from one peer to another one? What is needed? Are there peers that can directly communicate somehow? Then think of an electromagnetic signal. What could happen during propagation when a signal travels inside a cable, fiber, or through open space? I gave you an example for collisions of symbols. So what could cause this? Can this happen in real life? I will come back how this could happen in fibers, fiber optics. Are there any other problems that can cause collisions? Synchronization. Why do we need synchronization? Why should the sender somehow be synchronized with the receiver? So, and also what is needed to transmit data. Remember the definition of data, of signals, and also of information. And I have already briefly touched the analog to digital converter. So you remember our world outside is an analog world, but inside, in our computer, well, the world is digital. What is the difference? What do we need to come from analog to the digital world? Which parameters can we set here? So there are two major functions we need for this conversion of analog into digital world.